Okay, so before we start, I want to say that there's some real potential for injury with this experiment, so please be careful. You're going to be working with electricity, you're going to be working with water, you're going to be working with hot water, you're going to be working with electrical elements that heat up, so be careful, and if there's anything that scares you, make your lab instructor do it instead. Another thing to be aware of is that the way that we're hooking up the circuit in this experiment is actually a violation of the electrical code, so please don't think that you can wire your house just because you've done this experiment. You can't. Oh my gosh. Taking apart the circuit at the end of the experiment is part of the experiment. If you don't do it, you would lose some marks. They can be significant. So do take things apart, but please remember to unplug the circuit before you start attacking it with the screwdriver. Oh my gosh, don't start touching it while it's still live. Unplug it, then take it apart. The circuit will be checked twice by your lab instructor, so I'll tell you where, but you build the circuit, and before you put the face plates on the electrical sockets, you would bring it over to your instructor. They would check it out to make sure it looks okay electrically. Then you'd go back, put the face plates back on it, bring it back for a second check, just because we want to make sure that no wires got bumped loose when you put the face plates on. And if it looks okay on that second check, then your lab instructor will be the first person to actually plug something in. So if there's fire and smoke, it'll be the lab instructor's fault, not yours. Just make sure that you are not the first person to plug stuff into this. It gets checked twice by the lab instructor, and then they will plug it in for the very first time and test it. So question 1 is meant to be done as a class exercise, and it's actually not worth any marks. But you want to pay attention to how it's done, because you're going to be doing a whole bunch of calculations just like this later in this experiment, and they will be worth marks. So, question 1 says, assume we have a 500 watt stereo, calculate the energy that it'll use up in 1 hour, and also calculate how much it would cost to use that stereo for 1 hour, assuming that BC Hydro is charging us 6.7 cents per kilowatt hour. And I'll just pause there and mention that kilowatt hour is a unit of energy. It's kind of a weird unit of energy, but it's a unit of energy just like joules are. I'll also note that watts are equal to joules per second. So the unit of power, a watt, is just a measure of how much energy is being transferred. So joules per second, that's how much energy is transferred per second. So the first question is the energy it will use in an hour. So what is that? Well, let's first of all stop thinking of this as watts and think of it as joules per second. So 500 watts equals 500 joules per second, and the question wants to know how many joules do we use up in 1 hour. So it's just a matter of converting from seconds to hours. So to do that, we just multiply by 60 seconds per minute and 60 minutes per hour. And so you can plug this into your calculator now and calculate how many joules this stereo uses in 1 hour. Now, there's another way to calculate energy. So remember that I said kilowatt hours are also a unit of energy. I'm going to do that as well. So this is exactly the same calculation we've just done, except that my final answer is going to be in kilowatt hours instead of joules. So again, we start with 500 watts, 500 watt stereo, and we want to know how much energy it's going to use in an hour. So we want to convert this to kilowatt hours. So first of all, I'll go from watts to kilowatts. So multiply by 1 kilowatt equals 1,000 watts. And then I multiply by 1 hour because I want to go to kilowatt hours. So I can calculate this out. It's just going to be 0.5 kilowatt hours. Now this number here is exactly the same as the number you would have gotten up here, except it's in different units. So 0.5 kilowatt hours equals however many joules you calculated here. It's the same thing. The reason why I've done it this second way is that this actually makes it really easy to do question B. So question B says, how much would it cost to use the stereo for 1 hour if we're being charged 6.7 cents per kilowatt hour? So if I know how much energy we used up in kilowatt hours, I can just multiply by 6.7 cents per kilowatt hour and get my answer. So that's question B. So up here, I calculated how much energy we used in 1 hour with that stereo in joules. The second line here calculates the same quantity except in kilowatt hours, and I did that specifically because it then makes getting the answer to be very simple. You just take that answer and multiply by the 6.7 cents per kilowatt hour. Okay, in this experiment, basically you're going to be building some electrical sockets, putting them together, wiring them, and then you'll plug things into those outlets, and you'll see how much current is drawn through those appliances, and you'll draw some conclusions about it. So the outlets are going to be wired into these two little yellow boxes. You've been given a box full of equipment. Feel free to rummage through that. So one of the things you're given in this green case is a meter for measuring the current. So this has got a setting on it that says A with a little squiggle beside it because we're looking at alternating current today. So you would turn it to the A, and I'll show you in a moment how you actually attach this to your circuit. But over here I'll just note that on the side there's these two buttons, you squeeze them and that opens the clamps. Next thing you've got in here, this is a screwdriver with various heads. So you push the little button up, it pops up a screwdriver head for you. If you push the button down, it slurps it back in, and you put up a different one. These things are prone to jamming, so if your screwdriver jams, violence is the key. Do that to it, usually that'll clear the jam and it'll start functioning normally again. These are the two outlets that you're going to be wiring into the yellow boxes. The lab manual actually has very clear instructions for how to do that. So I'm not going to tell you too much about how you wire this. I will give you a few tips, but for the most part you just follow these instructions and you should be fine. I will note, however, that, just ignore my scribbles here, you're going to get your circuit checked twice by the lab instructor. So you build it to this point where everything's put together except for these face plates. So everything's wired up except for the face plates. You get that electrically checked by your instructor. If they think it looks okay, then you take it back to your desk, you put the face plates on, you take it back to the instructor for a second check. If everything looks okay again, then they're going to be the person that plugs in your electrical outlets and then plugs in an appliance and turns it on and sees whether or not this works, hopefully without anything dramatic happening. So like I said, your instructor checks your circuit twice. The first time when the face plates are not on, and the second time when the face plates are on. In your box, you've got two wires. So there's a plug wire that's got the plug attached to it here, and you've got what's called a continuing wire. So I'm going to show you in the video how these attach to the yellow boxes. The short answer is that the continuing wire goes between the two yellow boxes, and then the plug wire comes out the end here. And last thing I'll note about all of this is if you look right at the end here, at the ends of these yellow boxes there's these little trap doors, a little bit hard to see, but that's where you feed the wires in. So the first thing you're going to do is you take the plug wire, the one that's got the plug attached to it, and you take the end of it that has the loose wires sticking out, you feed it through this trap door so that the ends of the wires, all three of those, are sticking up out of the yellow box. Then I'll show you next how to hook up the continuing wire which connects these two yellow boxes together. Okay, so here's the circuit now with the continuing wire attached. So before I had the plug wire attached here, the wires feeding up through the yellow box. Now I've got the continuing wire just connecting these two boxes together. So this end comes down through the trapdoor, and these are the wires attached to this continuing wire. And over here, same thing, continuing wire goes in through the trapdoor, and just the ends of the wires come out here. So you've got one wire connecting these two boxes together, and then another wire with the plug attached to it on the other end. Okay, here's a trick for attaching the wires to this outlet. So grab your wire, and if necessary you take your needle nose pliers and you bend this guy into a half loop. So like that. And then what you do is you'd hook this over the appropriate screw, like so. And then you grab your screwdriver and you tighten this screw down to clamp the wire in place. So that becomes fairly stable once it's clamped. Now just a reminder that when you get your circuit to this point, where the sockets are attached but the face plates are not on, that's when you take it to your lab instructor to get it electrically checked. And if that checks out, they'll send you back to your desk, you put the face plates on, and then you bring it back to them for a second check. In other words, when it looks like this, with the face plates on, you get your second check from the lab instructor. And if everything looks okay electrically, then your lab instructor will plug in this and then plug something into these sockets and turn it on to make sure that the power is running to it properly. If that's all okay, then you'll be sent back to your desk to continue with the rest of the experiment. And you want to plug this guy into the power outlet that's dangling from the ceiling. Don't use the power bars on the edges of the desk because they've got a lower current rating and you're likely to pop the breakers on, or pardon me, pop the fuses on those guys. So I'm going to give you some very mild hints on how to do questions 3, 4, and 5. The reason why is that it's quite common by the time you do this experiment for you to have not taken this stuff in class yet. So I'll just give you a few mild hints to help you get through these. I'll also mention that the Kirchhoff's Law experiment also has an optional video that is supposed to help you do your pre-lab. It might be useful to watch that video in advance of this experiment too. So question 3 says, in the circuit you've connected, the black wire is hot. That is, it's got a high voltage. What's the function of the white wire and the bare copper wire? So the big hint I'll give you here is that though they mention voltage, this question's all about current. So current means electrons that come out of the wall, through the wires, through your appliance, back out through a different wire, and then back to BC Hydro. So current is little physical bodies moving in and out of your circuit. They need to go in via one path and out via another path. So 2 of the wires that we're talking about have electrons, have current flowing through them. There's also a 3rd wire that is meant to act as a fail-safe. The idea is that if you had a hot wire pop free inside a device and touch the outer casing, that'd be quite dangerous for somebody who then went and touched that appliance. So you have another wire that its job is to pull current that has gone where it's not supposed to go back out to ground so that it can't hurt people who then touch the device. So question 3, you need to think about current rather than voltage. So question 4 asks, why does it not matter which screw we attach the wire to on the outlet receptacle? So for example, if I attached a wire to this screw, both slots on this outlet would still get electricity. And why is that? They point out here that there's a metal plate connecting those 2 screws together. That's the key here. Think about that and you should be able to answer the question. So question 5 is a hypothetical question, and what they're asking is, what would happen if you touched various prongs on a partly exposed plug? Now obviously you should never do that. That can be incredibly dangerous. But they're asking you to think about which ones hypothetically would be dangerous to touch and which ones would be hypothetically safe to touch. And obviously never touch any prong on an exposed plug. So question A is which ones would give you a shock, and question B is which ones would not give you a shock. So there's 3 prongs. There's a tall rectangular one, a short rectangular one, and a round one. It's helpful for question 5 to think about your answers for question 3. So which wires are carrying current, which wires are just there as a fail-safe. So think about that and then answer question 5. Now in the next part of the lab you need to start plugging in appliances to your circuit. So unfortunately we just have 1 class set, so everybody in the room will have to share these. Generally speaking, you're only going to need to study 5 appliances. We actually have 6 here, so these are the ones you're likely to see. Toaster, heater, kettle, iron, hair dryer, and light bulb. So, as I said, you and everybody else in the class is going to have to share these. These appliances will either be on a spare desk or they'll be on a cart waiting for you. Now, one of the things you're going to need to do in the experiment is measure the current. And how do you do that? Well, first of all, go and look at your plug, and you'll notice that there's some exposed wires here. So, not electrically exposed, but the outer casing has been cut away. And so there's 3 things exposed here: black wire, a white wire, and the ground wire, which is just bare copper. So in order to measure the current, what you do is you take this guy, and remember you press these little switches on the side and it opens up the clamps, and you want to clamp onto either the white wire or the black wire, not both, just one of them. And then you turn it to the A setting, and you can just let this dangle when you plug it in up above, and then if you plug, say, a toaster into here and turn it on, then you'll be able to read how much current is being drawn by that toaster on this screen here. So this device here allows you to measure how much current is flowing through this wire. Okay, so now you've selected an appliance, and the first thing you want to do is find its power rating. So that will be written on the device somewhere. Right here it's actually embossed in the plastic. And what you're going to do is you're going to plug this guy in. And you're going to have this end, your plug, plugged into the power box above your desk, but I've left it here so you can see it. And this meter will be just dangling from it, set to the A setting. And when you turn this guy on to its maximum, which you should do for all of the ones that heat up, turn them to their maximum setting, then you should see how much current they draw. If this number fluctuates a bit, then write down the highest value that you see. Be aware also that if the previous group was using this and it's still hot, you may need to wait for it to cool down a little bit before you get the maximum power rating. And once you've done that, once you've got your current, they tell you calculate the energy used in 1 hour by this appliance, and then calculate the cost of using that appliance for 1 hour. So this is exactly the same calculation that we did in that sample calculation in question 1. So you're just doing it again, except this time for marks and with this appliance's power rating as you've read it. Then they ask you to calculate the predicted current for this appliance and the percent difference between the predicted current and the current that you actually measured using the meter. So to get the predicted current, you're just going to use the equation P, power, equals I, current, times V, voltage. So voltage is the 120 volts that BC Hydro gives us, and the power is what you read off of the side of the appliance. So current is the only thing that you need. You can solve for that. And then you compare to the value you actually got with the meter. Next, you're going to repeat this with all of the other appliances. So 5 appliances in total. You go and you plug each of them in, get the power rating, and measure the current. And then for each of them, you make a table, and in that table you would put down the power rating, the appliance name, the cost of using the appliance for 1 hour, the predicted current, the actual current, the one you measured, and the percent difference between the two of them. So you just repeat all of those calculations for all the other appliances also. And then they say comment in a few words about the agreement between the predicted and measured currents. So were the differences less than 5%? And can you suggest reasons for why there might be discrepancies? Now you're going to plug in 2 appliances at the same time, and they specify that you want to try and have low current appliances that you do for this part of the experiment. That's just so that there's less likelihood of you blowing the circuit breaker. So the light bulb is the lowest current one, so you plug this guy in along with some other appliance, and you measure how much current they draw together. First you actually predict that, and then you plug it in, you measure it, and then they tell you repeat it for another set of appliances. So you would have a table here with 1 pair of appliances, predicted current and actual current, and then a second set of appliances, predicted current, actual current. And then they say, what pattern do you notice in the data? Comment briefly. And then they tell you, predict what would happen if you plugged in 3 appliances at the same time. And then you confirm your prediction by actually plugging in a 3rd appliance. And again, aim for the low current ones just so that you don't blow a circuit breaker. So you make a quantitative prediction, so an actual number of what you think the total current's going to be, then you measure it. And again, you make a table of all this information. In question 17, they have a picture of a light bulb and a picture of a toaster, and they actually show you the wires inside the appliances. So you can actually see the wire running through the toaster and through the light bulb. And they tell you redraw those pictures on the circuit diagram below. So down here you've got a diagram of a plug, and again you can actually see the wires all the way through, including up to the outlets, and note that the two slots in the outlet, the wires do not connect there, so there's a little gap between them there. So they're telling you, take this light bulb and this toaster, redraw it down here. So redraw the light bulb, redraw the toaster, draw them actually plugged in. And then you're supposed to use small arrows to indicate how the current flows through these two circuits. So you should draw lots of arrows on here showing how the current moves in the wires and also how it moves in the devices. So make sure you draw arrows in the light bulb and in the toaster that you drew down here. So you show the entire current path going through the whole circuit. So questions 18 and 19 should be fairly straightforward for you to answer because they're very much based on what you just learned in the experiment regarding plugging in two or more appliances and how much current you expect the circuit to draw when you've got one or two or more appliances plugged in at the same time. So I won't say too much about how to answer these. You should be well equipped to answer them yourself at this point. Questions 20 and 21 have to do with how much current it takes to blow the circuit breaker in your house. And specifically, they ask if you have these devices, and they give you 4 of them, and they're all plugged in at the same time to the same circuit, are you going to trip your circuit breaker? And question 21 asks how many light bulbs could you plug in without tripping the circuit breaker? So again, these are fairly straightforward. You should be well equipped to answer these.